Sometimes the universe does not speak in words. It speaks in waves. The ocean moves in waves. Light travels in waves. Even our thoughts move in waves. From the smallest atom to the largest galaxy, everything vibrates. Welcome to Shellz Diary, where we explore the universe through steam and slope. Today we decode one of the deepest secrets of nature: waves. A wave is not matter traveling. It is energy traveling through space or through a medium. Imagine holding one end of a rope. You shake it gently, and a pattern moves along the rope. But the rope itself does not travel forward. The energy moves. The pattern moves. Every wave has three essential properties: amplitude, frequency, and wavelength. Amplitude tells us how strong the wave is. Frequency tells us how many oscillations occur in 1 second. Wavelength is the distance between repeating points in a wave. These ideas connect through a simple equation. V equals F lambda. Ultraviolet radiation is an electromagnetic wave. It can travel through empty space. When the wavelength is about the size of an atom, the radiation belongs to the X-ray region. Across science, philosophy, and psychology, we see the same idea again and again. Everything vibrates. Our brains produce electrical rhythms called brain waves. Our hearts beat in rhythmic pulses. Even atoms vibrate with energy. Sometimes the universe whispers, not through words, but through oscillations. From atoms to galaxies, nature writes its poetry in the language of waves. So, what exactly is a wave? In simple terms, a wave is a disturbance that transfers energy from one place to another. But here's the fascinating part. The medium itself does not actually travel with the wave. Instead, the particles simply oscillate around their original positions. Imagine a stadium full of people. One person stands up, raises their hands, and sits down. Then the next person does the same. And the next. Soon, a ripple of motion travels around the entire stadium. But the people themselves never move from their seats. This is called a stadium wave. In physics, a wave behaves in a very similar way. Energy travels. The particles stay. Wave. The two major types of waves. Physicists divide waves into two major categories. Mechanical waves. Mechanical waves need something to travel through. We call this a medium. The medium could be air, water, or even a stretched spring. For example, water waves moving across the ocean, sound waves traveling through air, or vibrations moving through a slinky toy. Without a medium, mechanical waves simply cannot exist. Electromagnetic waves. Electromagnetic waves are very different. They do not need a medium at all. They can travel through empty space. In fact, they are made of oscillating electric and magnetic fields. These waves include visible light, radio waves, microwaves, ultraviolet radiation, X-rays, and gamma rays. This is how sunlight travels across the vast emptiness of space to reach Earth. Waves can also be classified based on how particles move compared to the direction of energy transfer. Transverse waves. In a transverse wave, the motion of particles is perpendicular to the direction of energy travel. In other words, the particles move at 90 degrees to the wave direction. Imagine holding a rope and shaking it up and down. The rope moves vertically, but the wave travels horizontally. This is a classic example of a transverse wave. Light waves also belong to this category. Longitudinal waves. Longitudinal waves behave differently. Here, the particles move parallel to the direction of energy transfer. Instead of moving up and down, the particles compress and expand. This creates two distinct regions: compressions where particles are close together and rarefactions where particles spread apart. Sound waves moving through air are the perfect example of longitudinal waves. When someone speaks, the air particles vibrate back and forth. Those vibrations travel outward as sound. From ocean waves, to sound waves, to the light from distant stars, waves are everywhere. They carry energy across space, across oceans, and across the universe. And once we understand waves, we begin to understand the language of nature itself. Water waves and slinky waves. When we first study waves in physics, we often use simple models to understand complex natural phenomena. One classic example is the transverse wave on a slinky spring. Another example is the ripples on water when a stone is dropped into a pond or lake. At first glance, these two waves appear very similar. Both show a repeating pattern of peaks and valleys moving through space. But if we look more carefully, we discover an important difference. The motion in a slinky wave. In a slinky spring, each coil moves in only one dimension. When a transverse wave travels along the slinky, the coils simply move up and down. The energy travels along the spring, but the coils themselves stay near their original positions. This makes the motion easy to visualize and analyze. That is why physicists often use the slinky wave as a model when teaching wave motion. The motion in water waves. Water waves, however, behave differently. Although the surface of the water looks like a simple transverse sine wave, the motion of the water particles is more complex. In deep water, the individual water particles do not simply move up and down. Instead, they move in circular or elliptical paths. Each particle rotates in a small circle within a vertical plane. As these circular motions propagate through the water, they create the familiar wave pattern we see on the surface. This circular motion of particles produces the characteristic crest and trough pattern of water waves. Waves on the surface and in the bulk. When a disturbance occurs in a liquid, such as when a stone is thrown into a pond, waves spread across the surface. These surface waves are easy to observe. However, waves are also traveling within the bulk of the water beneath the surface. These internal waves are less visible but still play an important role in the overall motion of the liquid. Why physicists use models? You might wonder why physicists simplify such complex motions. Why do they use models like the slinky wave? The answer is simple. Physicists create general models so that the same principles can be applied to many different systems. A simple model helps us understand the fundamental behavior of waves. Once the concept is clear, the model can be expanded to describe more complicated situations. This is why the same wave concepts can describe vibrations in a spring, ripples on water, sound waves in air, and even light traveling through space. The universal idea of waves. So whether we look at a slinky spring, or the surface of a lake, we are witnessing the same fundamental phenomenon. Energy moving through a system while the individual particles simply oscillate around their equilibrium positions. Different systems, different motions, but the same underlying principle. That is the beauty of physics. Key wave definitions. Before we go deeper into the world of waves, we need to understand a few key definitions. These ideas form the basic language of wave physics. Once we understand them, we can describe almost any wave in nature. Frequency. First, let's talk about frequency. Frequency is the number of oscillations produced by a wave source in 1 second. In simpler terms, it tells us how many waves pass a particular point every second. For example, if 3 crests pass a point in 1 second, the frequency is 3 Hz. The unit of frequency is the Hertz, abbreviated as Hc. Higher frequency means more oscillations each second. Lower frequency means fewer oscillations. Wavelength. Next comes wavelength. Wavelength is the shortest distance between 2 points that are in the same phase of the wave. In practical terms, this means the distance between 2 consecutive crests or 2 consecutive troughs. This distance represents one complete wave cycle. Wavelength is usually represented by the Greek letter lambda, written as lambda, time period. Another important quantity is the time period. The time period is the time taken for one complete wave cycle. In other words, it is the time required for one wavelength to pass a fixed point. It is also the time taken for a particle in the medium to complete one full oscillation. The time period is represented by the symbol T. Frequency and time period are closely related. If the frequency increases, the time period becomes shorter. Amplitude. Now let's talk about amplitude. Amplitude is the maximum displacement of a particle from its equilibrium position. In simple terms, it tells us how far the particle moves from its rest position. For a transverse wave, the amplitude is the height of the crest above the equilibrium line. Amplitude often determines how strong or intense a wave appears. For example, a loud sound has a larger amplitude than a quiet sound. Wave speed. Another key concept is wave speed. Wave speed is the distance a wave travels in 1 second in its direction of propagation. This speed depends on the properties of the medium through which the wave travels. For example, sound moves faster in water than in air. Wave speed is usually represented by the symbol c. Understanding waves becomes much easier when we represent them using graphs. Physicists commonly use 2 types of graphs to visualize wave motion. Displacement distance graph. The first type is a displacement distance graph. This graph shows how the displacement of the medium varies with distance along the wave at a single moment in time. For a transverse wave, this graph looks like a snapshot or photograph of the wave shape. You can clearly see the crests and troughs along the wave. Displacement time graph. The second type is a displacement time graph. This graph shows how the displacement of one particular particle in the medium changes with time. Instead of showing the shape of the entire wave, it shows how a single point moves during oscillation. Important observation. When working with wave graphs, it is extremely important to look carefully at the axes. You must always check whether the graph represents distance or time. This tells you what the graph is actually describing. You must also consider the type of wave being represented. Is it a transverse wave, where particles move perpendicular to the wave direction? Or a longitudinal wave, where particles move parallel to the direction of energy transfer? Understanding these details ensures that the graph is interpreted correctly. With just a few definitions, frequency, wavelength, time period, amplitude, and wave speed, we gain a powerful toolkit. These ideas allow us to describe waves in oceans, vibrations in springs, sound traveling through air, and even light crossing the vast emptiness of space. Different systems, different scales, but the same elegant language of waves. Displacement distance graphs, wave representation. A displacement distance graph shows the shape of a wave at one instant in time. Vertical axis, y-axis, displacement of particles from equilibrium. Horizontal axis, x-axis, distance along the wave. So the graph is basically a snapshot of the wave in space. 1. Transverse wave representation. In a transverse wave, particles move perpendicular, 90 degrees, to the direction in which the wave travels. Examples: water surface waves, light waves, waves on a string. If the wave travels horizontally, the particles move up and down. What the graph shows. From the displacement distance graph we can directly read: amplitude, A, the maximum displacement from equilibrium. Wavelength, lambda, the distance between two identical points, crest to crest or trough to trough. The mathematical form often looks like a sine wave, important point. This graph does not show time. So from this graph we cannot determine time period, t, frequency, f, because those require time information, not just position. Longitudinal wave representation. In a longitudinal wave, particle motion is parallel to the direction of wave travel. Examples: sound waves in air, compression waves in springs. Here particles move forward and backward along the same direction as the wave. What the graph means here. The graph may look similar to the transverse wave graph, but the meaning is different. Instead of up-down motion, positive displacement right-pointing arrow particle moves forward. Negative displacement right-pointing arrow particle moves backward. The diagram often shows equilibrium, rest, positions of particles. Displaced positions caused by the passing wave. These movements produce compressions and rarefactions. Compression. Particles close together. Rarefaction. Particles spread apart. Key idea: even though the graph looks sinusoidal, the actual wave is not physically up and down. The graph simply shows how far particles move from equilibrium along the wave direction. In the previous discussion, we looked at displacement distance graphs, which show the shape of a wave in space. Now we explore something different. A displacement time graph tells the story of how one particle moves as time passes. Understanding the axes. In a displacement time graph, the vertical axis, y-axis, represents displacement of the particle. The horizontal axis, x-axis, represents time. So instead of seeing the whole wave at once, we focus on one particle and observe how it oscillates. Wave evolution over time. Imagine taking snapshots of a wave at time intervals of 1/4 of the period, t4. Each snapshot shows the wave slightly shifted forward. But something fascinating happens. Even though the wave moves forward, each particle simply oscillates around its own position. Particles do not travel with the wave. Energy moves, but matter mostly stays where it is. Points on the wave: P, Q, and R. Let's mark 3 points on the wave: P, Q, and R. Their motions reveal the concept of phase difference. P and Q are 180 degrees, pi radians, out of phase. When P is at a crest, Q is at a trough. Q and R are 90 degrees, pi, 2 radians, out of phase. Their oscillations are shifted by 1/4 of a cycle. Therefore P and R become 270 degrees, 3 pi, 2 radians, out of phase. These phase relationships describe how different particles in a wave move relative to each other. How the wave moves. If we connect the same zero displacement point in each snapshot of the wave, a straight line appears moving forward. This line reveals the illusion of wave motion. The particles themselves only vibrate, but the pattern of displacement travels through space. In one complete time period t, the wave moves forward by one full wavelength lambda. This leads to one of the most beautiful relationships in physics. V equals F, lambda. Where V equals wave speed. F equals frequency. A wave is a strange traveler. The particles remain, yet the motion journeys forward. Matter vibrates, energy migrates, and the universe whispers its rhythms through oscillations. What are sound waves? Sound waves are mechanical longitudinal waves produced by vibrating objects and transmitted through a medium such as air, water, or solids. They carry energy, not matter. Examples of sound sources: human voice, musical instruments, loudspeakers, vibrating machines. When an object vibrates, it pushes and pulls the surrounding particles, creating a wave of pressure variations that travels through the medium. Nature of sound waves. Sound waves are longitudinal waves. This means the particle motion is parallel to the direction of wave travel. They consist of two main regions: compression, high pressure. Particles are close together. Rarefaction, low pressure. Particles are spread apart. The sequence of compressions and rarefactions moves through the medium as a traveling wave. Medium required for sound. Sound waves need a material medium to travel. Because there are no particles in vacuum, sound cannot propagate in space. How sound is produced? Sound is produced when an object vibrates. Examples: guitar string vibration, vocal cords vibrating, loudspeaker diaphragm moving. The vibration causes alternating high and low pressure regions in the surrounding medium. How we hear sound. The process of hearing involves several steps. 1. Sound waves enter the outer ear. 2. They vibrate the eardrum. 3. Vibrations are transmitted through middle ear bones. 4. The cochlea converts vibrations to electrical signals. 5. Signals travel through the auditory nerve. 6. The brain interprets them as sound. The human ear is extremely sensitive. Smallest detectable pressure change, 2 × 10 raised to power -5 pascals. 8. Types of sound based on frequency. Infrasonic waves. Frequency less than 20 Hz. Examples: earthquakes, elephant communication. Audible sound 20 to 20,000 Hz. This is the human hearing range. Ultrasonic waves. Frequency greater than 20,000 Hz. Used in medical ultrasound, sonar, cleaning instruments. Important wave phenomena in sound. Reflection. Sound bouncing off surfaces. Example: echo. Refraction. Sound changes direction due to change in speed in different media. Diffraction. Sound bending around obstacles. Interference. When two sound waves meet and combine. This follows the principle of superposition. The nature of electromagnetic waves. Electromagnetic waves are waves of energy that travel through space in the form of oscillating electric and magnetic fields. Unlike mechanical waves such as sound waves, electromagnetic waves do not need a material medium to travel. They are able to move through empty space, which is why light from the sun can reach the Earth across the vacuum of space. Electromagnetic waves are transverse waves. This means that the oscillations of the fields occur perpendicular to the direction in which the wave travels. In an electromagnetic wave, a changing electric field and a changing magnetic field exist together. These two fields are at right angles to each other and also at right angles to the direction in which the wave is moving. The electric and magnetic fields reach their maximum strength at the same time as the wave passes through space. All electromagnetic radiation travels at the same speed in a vacuum, known as the speed of light. This speed is approximately 3.00 times 10 to the power of 8 meters per second. When electromagnetic radiation moves from a vacuum into another medium such as glass, water, or air, its speed changes and its wavelength changes as well. However, the frequency of the radiation remains constant. Electromagnetic waves are produced when charged particles accelerate or when electrons change energy levels inside atoms. When these changes occur, energy is released in the form of electromagnetic radiation. This radiation can appear as radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, or gamma rays. Human eyes can detect only a very small part of this range, which we call visible light. The intensity of electromagnetic radiation decreases as the distance from the source increases. As the wave travels outward, its energy spreads over a larger area of space. Because the same amount of energy is distributed across a wider surface, the radiation becomes weaker with increasing distance. Understanding the nature of light and electromagnetic waves was difficult for scientists in earlier centuries. Different ideas were proposed, including the view that light behaved like tiny particles. Later, the work of scientists such as James Clerk Maxwell showed that light could be described as an electromagnetic wave consisting of electric and magnetic fields. Today, scientists recognize that light can behave both as a wave and as a particle. In many situations it behaves like a wave, showing properties such as interference and diffraction. In other situations it behaves like a particle called a photon. Because of this dual behavior, light is understood through both wave theory and quantum theory. Electromagnetic waves therefore form a fundamental part of modern physics, explaining how energy travels through space and how light and radiation interact with matter. And so, as our journey through waves comes to an end, we realize something extraordinary. The universe is not silent. It is a grand symphony of vibrations. From the whisper of sound moving through air, to the invisible electromagnetic waves traveling across the vast emptiness of space, everything around us is in motion, in rhythm, in resonance. Waves carry energy, information, and sometimes even meaning. They connect atoms to galaxies, technology to humanity, and science to wonder. Through steam, we saw the elegance of physics, mathematics, engineering, and art woven together in the language of oscillations. Through slope, we glimpsed something deeper, the waves of thought, emotion, knowledge, and consciousness that ripple through the human experience. Perhaps the most beautiful truth is this: just like waves spreading across the ocean, ideas begin as small vibrations, and then travel outward, touching minds far beyond their origin. So the next time you hear a sound, see a beam of light, or feel the rhythm of music, remember, you are not just observing waves. You are part of the universe's eternal rhythm. This is Shellz from Shellz Diary, where science meets philosophy, and knowledge becomes a journey. Until the next wave of discovery.